Who doesn't like growth in their career? And even if more, if the growth is in exponential form, it becomes mesmerizing. So today we will be studying about the exponential function and its special form. It will be logarithmic function. Disclaimer: this is not a career guide channel. It will be completely based on mathematics. Presenting you with exponential and logarithmic function. So let's see. First of all, what is exponential function? So as you can see here, we have written a function as fx equals to b to the power x. B must be a kind of constant considered as base, and to the power x, that x is the exponent or the power of b. If the value of b is 1, then the function will be continuously increasing nature. The slope of the function will be continuously increasing. So let's take an example. Here we have taken fx equals to 2 to the power x. So with respect to x, we write down all the values of x. For x equals to minus 2, minus 1, 0, 1, 2, 3, and the function goes on, the value. So it will be 1 by 4, 1 by 2, 1, 2, 4, 8. So now let's plot this function. So as we begin to plot, as you can see here, the points we have obtained in our last moment, that will be 1 by 4 for minus 2 value, then half for minus 1 value, 1 for 0, then for value x value 1 we obtain 2, for x value 2 we obtain 4, and then the graph goes on. Now it is going out from the screen. So let us plot the curve. So as you can see here, it is a continuously increasing function, and exponential curve is quite a great highly increasing nature of function. So this is the basic nature of an exponential curve. You can plot any exponential curve keeping any kind of base whose value will be greater than 1, and we are going to obtain this kind of nature. Irrespective that the points will be slightly different in their positions, but the nature of growth will be same. Now, we choose e as a common base for exponential function. You might have used somewhere, or you might have been knowing that fx equals to e to the power x is a common exponential function, but the value of e stands as 2.718. So I have approximated as 2.7 value. But have you wondered how we obtain the value e equals to 2.718? But why only e? So these are the questions must be surrounding and going around in your mind. So let's look into it. So here we come up with an idea and fact. A bank, and you are wise enough to invest in your bank. When your bank is giving you a scheme of paisa double in 1 year. So in 1 year you're gonna get double the amount you have invested. Depending on the reality check, none of the bank provide us with such a high amount of interest. So if you consider that you have invested a rupees 100 in your bank, and the bank is providing an interest rate of 100% with a compounding nature of 1 year. So within 1 year you're gonna get 2x, that is 200 as an return. So that would be really great. We could have continuously and very quickly increased our wealth, increased our property, and earns in crores. But now wait. If we start compounding in a smaller part, that is in 3 months, then we will find the amount will be around 2.44 into x. You may calculate out with the help of the compound interest formula that I have used here. So the value will be 2.44x, which is equals to 244. So it is greater than the amount when it was compounded in 1 year. Now let's increase the frequency of compound and make it in 1 month, and thus you obtain the amount as follows: 261. So you can really observe, as the compound frequency increases, the amount also increases. So I can say Both are directly proportional in their increase. And now let's make it down to 1 day, and hence the value also increases. It's around 2.71, that is 271 rupees. So it's quite difference you can obtain here when it was compounded in 1 year and rather it is compounded in a single day. So now you have observed and you have understood the fact that if we can compound the money at each and every instant, then the money will be much more higher. So we realize the frequency of the compound of the money is large, then we're gonna obtain higher amount of money. So let us consider n be the number of compound, and thus we come up with an idea that if the frequency n tends to infinity, so infinite number of times, that is in every instant we start compounding the money, we're gonna get a higher return. So now we try to obtain the value of this expression of 1 plus 1 by n whole to the power n, where n tends to infinity, using binomial expansion. So binomial expansion will help us to obtain it in a form of series as 1 plus 1 by 1 factorial, then 1 plus 1 by 2 factorial, then 1 plus 1 by 3 factorial, and the term goes on till we want, keep considering n as a very large value to obtain the exact value of this series. And thus we obtain the value as e equals to 2.718. The value of e was named after the Swiss mathematician Euler, and it is named as Euler constant. And the concept or the idea to obtain the value of e with the help of compound interest was also obtained by another Swiss mathematician, Bernoulli. And thus we can write the exponential function in a form of as fx equals to e to the power x. And you know the value of e as e approximately equals to 2.718. This comes as an helpful in various ways, such as it is easy in differentiation. So when we try to differentiate the function e to the power x, we obtain same as it is, and similarly for the integration also. So there are many specialities with this number and this form of function, and so it became an important part in mathematics. So I will mention one more thing, that if we try to plot the exponential function with different bases, like this one is plotted for base equals to 2, this one is plotted for base equals to 4, and the blue solid line is plotted for base equal as e, you will find that all the functions will try to meet at a point 0 comma 1, that is when the value of x is 0, the power or the exponent is 0, the value stands as 1. But if we draw a straight line right through the point 0 comma 1, keeping the slope as 1, we will find that it acts as a tangent only for the function e to the power x. So you can consider it as a specialty for it. So now presenting you with logarithmic function. So this is a special form of the exponential function which is used to express large numbers in a compact form. So let's see. As you look into the example is written as 2 to the power 3 that we obtain as 8. So when we use log, then we have to consider the base, where 2 is considered as base, and 8. Thus we obtain 3 as the result, that was the exponent of the last expression. So now how it is helpful, I'm going to tell you. First, they consider the fx, the function, as fx equals to log b, that is the base, and x. The most commonly used two bases are 10 and e, that is the exponential, that Euler number e. Why 10 is commonly used? Because throughout our course in science, we will find that we require to calculate numbers with power such as 10 to the power 8, 9, then 23, and many more. So these are few common examples that I have taken. Like for the speed of light, you require 10 to the power 8. For Avogadro number, you will be requiring around 10 to the power 22, 23, as such. So when those numbers can be expressed in a compact form, Like if we use log with base 10 and a number like 10 to the power 23, you don't require to write as a large form factor and can be in short written as simple 23 with a large number in a compact form. Now these are the few logarithmic laws which are in generally used, and it is compared with the set of laws for the exponential functions and for the logarithmic functions. On the right hand side, these are for logarithmic function, and on the left hand side, these are for the exponential functions. So here we took into consideration that b to the power mx be a kind of function has been considered as x, and b to the power n has been considered as y, and thus the laws follows as you can find that x into y a simple product, we obtain b to the power m plus n. Then x divided by simple division we obtain as b to the power m minus n. Then b, that is x whole to the power n, can be written as b to the power mn. Okay, then b to the power 1, where the value of m will be 1, we obtain same as b, and b to the power 0 as 1. Now when we look into the logarithmic functions which are counterpart of the exponential functions, we obtain as such log with base b, the base we have used here, that b, into xy, x and y product, we obtain as the summation of log x plus log y. Then we obtain log with base b x divide y as the subtraction of log x minus log y, and then as log of x to the power n, that is bm to the power n that was used, is written as this power has shifted and come in front, that is n, and thus we write n into log base b x. Then log similar with the value of base b and x, so both here repetition of the same number, we obtain the value as 1. And for any of different bases, if we try to obtain the logarithmic value of 1, we will be obtaining 0. And at last, we obtain one of the most important formula, right, to convert the basis of log function, and that is log bx is equals to log of ax, and the relation in between, that is log a of b. Do you know that ln x is equals to log with base value of ex, and if we write simply log of x, it is considered that its base value will be 10. Now we interrelate between ln x and log of x. You will find the relation as ln x equals to 2.302 of log x. We obtain this form of equation or this formula from the last formula that we have written in the chart, that is the conversion from one base of log to another base. Now we will try to plot the log x function, for which we have written down this table with different values of x and the log x as such. Now let's try to plot it. So as you can see the graph, that slowly this red dot started appearing on screen. So these are the coordinates or the point with respect to the values that I have written on the chart. So now if we join all these points and extrapolate, we will obtain the nature of the graph of log x. So simply by joining we obtain this green colored nature graph of log x. As you can see here, all these values will be very less than 1, and here the value is slowly increasing, and we will find that the value slowly increases and goes above 1, but for a very large value of x. So if we further extend this region further downward, we will find it will never meet the y-axis for the negative value of log x function. Moreover, we will never use negative value of x because it is undefined for any kind of logarithmic function. So if you like the content, give a thumbs up and share the video.